3. So you're given the values A1 to A2013, and they're chosen independently and at random from the set 1 to 2013. And so we want to find the expected number of distinct values in the set of A1 to A2013. So we can define a variable x event for n in 1, 2, 3, all the way to 2013, such that xn, and we define it so that xn is equal to either 1 or 0. And so it's 1 if n appears in one of A1, A2 to A2013, and 0 otherwise. And so we see that E of xn is simply the chance that n appears in the numbers A1 to A2013. Okay. So we can see that the expected value of the number of distinct values is simply, I'll just write expected value. It's simply equal to 2013 times E of x. And clearly, oh, and if you don't remember, E of x is the expected value of x. And so the reason for this is just because this E of x event is equal for all n, and the expected value is just the sum from n equals 1 to 2013 of E of x of x. So it's just, 2013 times E of x of x. And so we can see that this is simply just 2013 times the chance that n appears from A1 to A2013. And so the chance that n appears is simply just 1 minus the chance that n does not appear. And so the chance that n does not appear is simply just, we can calculate it individually for A1 to A2013. And of course, it's impossible for there to be an overlap, because if there's any instance from A1 to A2013 where this is false, then the whole thing is false. So the chance for all 2013 of the numbers is 2012 over 2013. Because there are a total of 2012 numbers other than n. And of course, we raise this, not n, to the power of 2013, because there are 2013 elements from A1 to A2013. And if we put this over a common denominator, this is simply just 2013 to the power of 2013 minus 2012 to the power of 2013, all divided by 2013 to the power of 2013. And so the answer that we wanted to find was simply 2013 times the chance that n appears and we can see that this is just equal to 2013 times 2013 minus 2012 to the power of 2013 over 2013 to the power of 2013, which is simply just 2013 to the power of 2013 minus 2012 to the power of 2013, all divided by 2013 to the power of 2012. Okay. And so that's our answer. So does anyone have any questions regarding this problem? I'll wait for a while for if there are questions. So let's move on to the next question. Level 4. So each cell of an n by n board is filled with some non-negative integer. So two numbers are said to be adjacent if their cells share a common side. And this, of course, is basically the standard definition of adjacent cells. And so the filling is called a garden if the following two conditions are satisfied. The difference between any two adjacent numbers is either 0 or 1, and if a number is less than or equal to all of its adjacent elements, then it's 0. Okay, and so we want to find the more distinct garden in terms of m and n. So we have a claim, and it's that any distribution of zeros will create a distinct garden. And of course, as long as there is at least one zero. Okay. Okay. So in order to prove this claim, we will basically make another lemma now. So for any non-zero cell, well, this technically can work as well for cells that have the element 0. It's just a lot more abstract. So for any non-zero cell, the value or the number in the cell, otherwise referred to as the value, so I'll just refer to it as the value from now on, is equal to the distance from the nearest 0. And in this grid of squares, the distance is a bit special. So what the distance here is referring to isn't the straight line distance. Instead, it's the number of cells that. So if the it's the shortest chain of cells that leads from a certain cell to the other. So basically, I can give an example. So here, the distance between these two shaded in cells is not this distance, which would be root 13. Instead, the distance is 4. Or sorry, 3. Because it passes through a total of 1, 2, 3 cells. Yeah. So that's what this lemma is meaning. So, of course, what I mean by this. So what I meant by this works for cells that are zero is just because you can technically define the distance from a cell to itself to just be zero. So yeah. So all cells with the values that are not zero will always have a cell with an adjacent cell with a value that is less than itself. And that's just because of condition 2. If the certain cell is the smallest or one of the smallest among all of its adjacent numbers, then this cell is zero. But we already are working with a cell with a value that is non-zero. So all cells with non-zero value will have an adjacent cell with less value. And so that means that the path from the cell of non-zero value to zero is always decreasing. And of course, now what we can use is condition 1. So condition 1, the difference between any two adjacent elements is either 0 or 1. Of course, we already confirmed here that the path is always decreasing, so the difference cannot be 0, which means that the difference is always 1. And so that means that that means that the value of any cell is equal to the distance from the nearest zero. Of course, if there are two zeros of the same distance, then the cell will just have the same value. We'll just have that common distance, assuming that those two are both simultaneously the shortest. And so what this means is that it is indeed true that the zeros determine the guard, because we can just start listing out the distances from the zeros and choose the smallest values for each of them. And that solves the problem. And so there are a total of mn cells, and there are technically two choices for each cell. Either the cell contains zero or it does not contain zero. And so that creates 2 to the power of mn ways of choosing the zeros in the cells. At the same time, though, we need to remember that it's impossible for all cells to be non-zero, because if all cells are non-zero, then condition 2 would be false. The reason being that if we take the smallest value among all of the integers, then this number is always less than or equal to all of its adjacent numbers, and by condition 2, that must be 0. But if we go by the assumption that there are no zeros, then this is obviously a contradiction. And so there has to be at least one zero. And so of these 2 to the power of mn ways to distribute the zeros, you can see that there is only one way in which there are no zeros, and that's literally by choosing to not have a zero in all mn cells. And so the number of ways to the number of distinct guardians is simply just 2 to the power of mn minus 1. So does anyone have any questions? Okay, well, if not, then I guess I guess we can have Larry Singh go over, start his lecture now if he wants, and you can override my screen share.